Okay guys, in this video we're going to be talking about combustion analysis, which is a way of determining the percent composition of certain types of compounds. We're going to be focusing on compounds that contain carbon, hydrogen, and oxygen, and the idea is to exploit a combustion reaction where that compound is burned in the presence of oxygen to produce carbon dioxide and water. Okay, and so this is not a balanced chemical reaction because we don't yet know what X, Y, and Z are. What I want to point out is that all of the carbon in this compound winds up in the carbon dioxide, and all of the hydrogen in the compound winds up in the water. So the idea of a combustion analysis is to capture both the carbon dioxide and the water and to measure their masses, and then convert the mass of the CO2 that is measured into the mass of the carbon that was found in the original sample. Likewise, you can measure the mass of the water that you've captured and convert that to the amount of mass in the original compound. And by this analysis, you can deduce what is the percent composition of carbon, hydrogen, and oxygen in this original compound. And here's an example of a diagram, at least, of an experimental setup. You have some material composed of carbon, hydrogen, and oxygen. You pass oxygen gas across that material in a furnace. Okay, so it's at an elevated temperature, which causes the sample to burn in the presence of oxygen. And then you have a vessel that is able to, that's packed with a substance that is able to absorb the water. Likewise, you have a vessel that is able to absorb the carbon dioxide. And then all of the other gases, they just pass on through. Now, if you measure the mass of these two vessels before and after the combustion reaction, you can take the difference in the masses to give you the mass of the water and the mass of the CO2 that was produced by the combustion reaction. And what I'm going to show you in the next problems is how to convert the mass of the water and the mass of the carbon dioxide into a percent composition for the unknown compound. So here we're going to be pretending that we don't know what acetic acid is. We do know that it's composed of carbon, hydrogen, and oxygen. And so we'll suppose that it has a formula that looks like this. Okay? And it's going to be burning in the presence of excess oxygen to give us CO2 and water. Now, that CO2 and water are collected, and it's found that a 4.24 milligram sample of acetic acid produces 6.21 milligrams of carbon dioxide and 2.54 milligrams of water. We're being asked to calculate the percentage of carbon, hydrogen, and oxygen in the original compound. So what we need in order to do that is to figure out what is the mass of carbon in the original compound, what's the mass of hydrogen in the original compound. So all of the carbon winds up in the CO2. So what we're going to do is take the milligrams of CO2 that we have, we'll convert it to grams, we'll convert it to moles of CO2, then we can convert it to moles of carbon, and then to grams and milligrams of carbon. Okay. This will give us the milligrams of carbon that are in that compound. You can take the milligrams of carbon, divide it by the mass of the sample, multiply by 100, and that's the percentage of carbon. Okay, so we're going to do that calculation. I'll set that up here. We're also going to do a similar calculation for hydrogen, milligrams of water to grams of water to moles of water. Then we're going to convert that to moles of hydrogen, then to grams of hydrogen, to milligrams of hydrogen. We can take that milligram of hydrogen, again divided by divide it by the total mass of the sample, multiply by 100, and that gives us our percentage of hydrogen. Okay, so let's set up those two calculations right now. We'll start with the 0. We'll just do it this way. We'll do 6.21 times 10 to the minus 3 grams of CO2. Okay? And to get the moles of CO2, we're going to need the molar mass of the CO2. So I'll calculate that really quick. And then we will divide by that molar mass. Okay, so that's going to give us the moles of CO2. There is 1 mole of carbon for every 1 mole of CO2. And then to get the grams of carbon, we multiply by the atomic mass of carbon, 12.01 grams per mole. And then we can convert that to milligrams. So 10 to the 3 milligrams per gram. So that'll be our milligrams of carbon. So I'm getting 1.69 out of that. Okay, we'll save that for later. Let's do the calculation for water. So for water, we had 2.54 milligrams. So I'm going to write that as times 10 to the minus 3 grams of water. The molar mass of water is 18.02 grams per mole. So I will take that and divide this grams by the molar mass of water. Okay. Then we'll convert that to moles of hydrogen. There are 2 moles of hydrogen atoms for every mole of water molecules. Then to get the grams of hydrogen, I'm going to multiply by the atomic mass of hydrogen. And then we'll take 10 to the 3 milligrams per gram so that we'll get our answer in milligrams of hydrogen. So I'm getting 0.285. Okay, so now we can calculate the percent carbon by taking the amount of carbon we found and dividing by the total mass of the sample, 4.24, multiplied by 100. We'll do the same thing for hydrogen. And that will give us 2 of the percentages. How are we going to get the percentage of oxygen? Well, we know that the percentages need to add up to 100, so it's going to be 100 minus the percent carbon minus the percent hydrogen. I'm getting 53.5% out of that. Okay, so that's how you use a combustion analysis to determine the percent composition of a compound that contains carbon, hydrogen, and oxygen. This next problem here, let's see. Yeah, this is the second problem here. So this is another problem involving vitamin C, which contains only carbon, hydrogen, and oxygen. It's solved in exactly the same way. The only difference is the mass of the sample, the mass of the CO2 that's produced, and the mass of the water that's produced. So if you replace all of those numbers with the numbers that I've used in this problem, you're going to get the correct percent composition for vitamin C. So I'm going to leave that one as an exercise for you to try on your own. And I'm going to pick up with thermochemistry, our next chapter, in the next video.